Okay, so today we are going to learn how to lay out NMOS and PMOS on Cadence. And the process of doing the design is, first of all, we do schematic design. Which we already learned. And today we are going to learn how to draw the layout so that the semiconductor company can fabricate what you want. And after the layout, we have to do several checks. First one is DRC. DRC means design rule check. Design rule check. For example, if we are using AMI 0.5 micrometer process, that means the minimum feature size is 0.5 or 0.6 micrometer. Sometimes we call it 0.5, sometimes we call it 0.6, because when you specify the length in Cadence, it's actually 0.6. But for some reason, some people would like to call it 0.5. Anyway, you can't draw something with 0.1 micrometer length. So that means design rule check. We have to make sure the thing you draw is fabricable. I mean, you can fabricate it. So first one is DRC check. After that, we have to do extraction. Extraction means we draw the layout, and the software will help us to figure out what does this layout mean. Physically, I just draw the gate, I draw the active region, and the software will help me to figure it out. Oh, this is a MOSFET I want. So after extraction, I have a corresponding circuit that is really designed, and based on that, we can do LVS. LVS means layout versus schematic. Schematic. So basically, we create 3 files in Cadence. The first one is schematic file. We have already done some exercise before, and today we are going to learn how to create another file, layout file. And based on the layout, we use the software to extract the extracted view of layout. And finally, we've got to compare if the extracted schematic is the same as the schematic we used in simulation. Does this make sense? Okay, so first of all, let's discuss the layout of MOS transistor. Number one is MOS. And I'll draw here the cross-section we have seen for multiple times. I have the P-type substrate, P-sub. And on the P-type substrate, I create N+, which is used for source, for example, left-hand side and right-hand side drain. And I have the gate above the P substrate. And between the gate and the substrate, we have the dioxide, which serves as insulator. And if the transistor is biased appropriately, we can form a channel underneath the gate, right? Oops. So this is a channel, and this is a gate. And finally, for the 4th terminal, because for a transistor we have 4 terminals: drain, source, gate, and also the body. We have to create another contact for the body. So this is a P+, makes an ohmic contact for body. And this is a cross-section, and in real layout, we have to extend those terminals to higher level of metals so that you can route the signal to the external of this chip, right? So I can grow this via, and this via connect my source to the higher level metal one, and the same thing for the gate. For the gate, I can grow something, and this is a via, or sometimes we call the whole thing as contact, to make a contact from metal 1 to the gate. And also for the drain, connected to metal 1. However, if we only have metal 1, the problem comes when we have too many wires, we may short them. So we can introduce even higher levels, like I can connect metal 1 up to metal 2. Metal 2. Like this, and even further to metal 3, metal 4. And in our process, AMI 0.5 micrometer, we have 3 layers of metal. Metal 1, 2, 3. And serving as an example for you, a reference, in the UMC 0.13 micrometer process, we have, we should have 8 layers of regular metal. So from metal 1 all the way up to metal 8. So this tells us why we can find job in semiconductor industry, because always the process keeps scale down, and we've got more advanced process. Okay. And also for the body, I have to make a contact to metal 1 or even to metal 2, metal 3. So this is a cross section. And in Cadence, when we draw the design, we do the layout, we are not draw the designing from the cross section view. Instead, we are looking at the design from the top of the chip. So in Cadence design, what we can see is we are looking down from the top of the chip. We will see something like this. This is the active region. And for the gate over there, for this gate, it corresponding to polygate like this, overlap with my active region, right? And the effective, let's say if this is my active region, then the effective gate section is actually denoted by the red line, like this. This is a gate. And we can measure the dimension of the gate. So this is the W we used a lot in our calculation. And this is a length, L. Alright? Same thing here. From the cross view, L corresponding to this dimension. Any question on this? Okay, so far so good. And let's look at the cross section. We have to make the source and the drain, right, from the active region, the P substrate. So that means we have to draw contact. Here I make 2 contacts. When I have a rectangle and a cross like this, it means a contact. And this contact connect the P substrate. Actually, should be the N plus inside the P substrate up to metal 1. So this tells the foundry that I'm going to have contact here for the source. So this is my contact for source. And on the other hand side, I can make contact for my drain, like this. Okay. So pretty much this is something we have for the transistor. However, we still have to route out the signal for the gate, right? The thing is, normally we don't make contact directly above the gate. Instead, we extend the gate poly, this is a polysilicon, to the outside, and we can make a contact over here. So make this contact to route signal from the gate polysilicon to metal 1, and you can even route it to metal 2 or metal 3. So this is a gate contact to higher level of metal. And finally, we have to take care of the fourth terminal, the body over here, right? So if, oops, this is a little too large. So if this box is my active region, then I have to make a contact for the P substrate outside my active region. So I can make contact over here directly above the P substrate, and this contact connect the P substrate to metal 1. So this is the contact for my body. And that's all. And once we make this contact, we can use metal. For example, if I use blue 9 for metal 1, then I can further extend the signal to the outside using metal 1, because I have contact to connect P substrate with metal 1, right? And for the drain, I can also use metal 1 to extend the signal. For the source, I can use metal 1 to extend the signal whatever I want. And for the gate, I can route the signal out, something like this, make a path. Okay, any question on this layout?
Why are we using two contacts for drain, source, and body?
Okay, the question is, why are we using two contacts for source, drain, and body? Actually, not necessary. As long as you have one contact, you can pass the DRC, extraction, and LVS. You can pass all the rule check, and you are actually effectively making the correct transistor. The thing is, the more contact you have, the less resistance you have. Because once you have contact, you will have resistive loss over those signal paths, right? So if you have two contacts, it means you have two resistors in parallel. Effectively, you make the resistance loss smaller. And this is very important for next semester, the microwave solid-state circuit. In that course, we will learn the effect of number of contacts on the gate. Actually, that will affect your noise performance, your gain performance a lot. When signal goes high, you have to minimize everywhere, minimize the resistance. Okay? Any other question?
How do you know that active region, the length of the active region?
The question is, how can we decide the length of the active region? So this big rectangle box is the active region, and this length is not very important. The most important figures is the length of the gate, this L, and the W, the width of the gate, because the performance is directly related to W over L, right? So theoretically, we can exaggerate it. You can make the active region very large, but in that way, you consume a lot of area. So finally, it's dependent on the size of the gate. If you have this width of the gate, then you have to make sure the active region should have the same width, right? And for the length, it's dependent on how large you can have for the contact. You can't make the contact infinitely small, so contact will consume the area. Okay.
How do you know that body is not in the active region?
The other question is, how do we know that the body is not in the active region? So you have to make sure this contact is outside of this rectangle of contact region, or of active region. Does this make sense?
Why is it outside the active region?
Pardon me?
Why is it outside the active region? Can't it be inside the active region?
Okay. The thing is, when you draw this rectangle, when you draw this one, it tells the computer and also the foundry that you want to make the active region this large. So once you tell the foundry the active region is this large, the only responsibility for you is to make sure the contact of body is outside this active region. Okay.
But what is it denoting? What does the active region denote?
Active region is something related to those N+. See, in the MOS, you have two N+ region.
So it's the doping window.
Yes.
But why don't we make two smaller ones?
Why don't we make it small?
Yeah.
Two separate, like doping.
Why do we have to have the active? Why can't we have one over the N+ and another one over the other N+?
Okay. The thing, this is actually decided by the foundry. When they define this kind of layout process, they made it simple, because either way, if you want to build transistor, you must have two active region, right? So you do this, and they have the gate overlapping your active region. So when you do doping, actually the N+ can't enter the area below the gate because it's blocked.
Right.
And this makes your life easier, because when you draw the layout, you only need to define one active region instead of two. That consumes less time for you, right?
Okay.
So the companies, they are trying to make the most efficient procedure for you to do the design. Okay?
But would they let you just make two active regions? Or...
I don't think so, because if you make two active regions, the software, a lot of times, it cannot recognize this as a transistor. You have to do extraction, and the rule for extraction is it has to identify one active region, and on the active region, you should have the polysilicon gate.
Okay.
Okay?
And how does, when we make a contact to the end well, does it know that it has to add additional doping at those points to make an ohmic contact?
The question is, how do we tell the company that we want to make additional doping? So actually, when you draw this active region, it's telling the software that they will identify where the company has to do additional doping for the transistor. And they will identify where is the contact, and they will implant the N+.
It's automatic. You don't
Yeah,
have to do that yourself.
Yeah, it's totally automatic. You don't have to do anything. You just need to draw this figure. Okay? Any other question? Okay. Then we will switch to Cadence to lay out the MOS. So in this Cadence example, I will draw an ugly MOS because this is our first class. So I will not tell you how to optimize the design. Actually, later on next week, I will tell you, even though we are designing the same thing, for example, if we are designing W equals to 10 micrometer, L equals to 1 micrometer, we have different ways to draw it out, and they will affect the performance. But today, I just want to show you how to draw a MOSFET that can pass all the DRC extraction and LVS. Alright? So we will make this as an example. Width is 10 micrometer and the length is 1 micrometer. And for our process AMI 0.5 micrometer, we have to find the closest possible value. So that will be 10.05 micrometer, 1.05 micrometer. Because the companies will define a snap grid, you can't make the values analog. You can't make something like 10.0001. That's impossible. Impossible for them to fabricate the mask. So their snap grid is 0.05 micrometer. So when you enter something like 10.001, it will round to the closest possible value. Okay? So let's see how we can do it in Cadence. I go to this library, class demo, and I will create a new cell, schematic cell first, MOS demo layout. And in this schematic cell, I put the MOS transistor using the NCSU analog part library for schematic design. Find the MOS transistor, MOS4, put it over there, and use a button Q to define the property. So here is an example. For example, if I want 10 micrometer and I go to next option, the program will automatically change it to 10.05 micrometer. Because this is something the company can really do for you. And for the length, I will change it to 1 micrometer. So that's all. And suppose I want to make some very typical connection for the transistor. For MOS, I will short the source and the body. And normally, I connect the source and the body to the ground, so I add a pin, ground. I hit a button P to add a pin, G and D. And this pin is input-output pin, because signal can go both ways. And I put this pin over there to connect this wire. And I have to design 2 other pins using the button P. The other pin is for the gate, so I name it as gate. And this is input pin, because normally signal enters the gate. And finally, I make the drain pin, define it as output pin, and makes a connection. So let's assume I have a very simple circuit like this. Now I close the schematic. I have to, this is the example I established the cell MOS demo layout schematic. And now I have to create another file for the layout. So I go to File, New, Cell View, same thing. But I have to change the tool over here. So on this list, I choose Virtuoso, the last option, Virtuoso. That means layout. And you can see the view name has changed immediately to layout, right? And I keep the same cell name. Click OK. Now I have 2 windows pop up. One is the LSW window. this window shows me all the layers I have in my process, in the AMI 0.5 micrometer process. For example, we can see N-well, active region, poly means polysilicon, metal 1, 2, 3, right? And I have this window, layout window. And if I look into my library, I will see under the cell MOS_demo_layout, I have two files now. One is schematic, another is layout. So I go back to the layout window. I add instance by hitting the button I. Hitting the button I and browse a library. And this time I have to use the library of ncsu_take_library_AMI06. This is a 0.5 micrometer process. Okay. And under this library, I go to the cell and choose the component MOS. And the view option is layout, which is correct. So I move the mouse into the layout window and put the component over there. At the beginning, it looks weird. This is the only thing I can see. So in order to show the real layout, I have to use the button Shift plus F. Shift F. I'll write down those bind keys for you. So add instance, it's I, and the show layout is Shift plus F. So now this is the layout of the MOS. Very straightforward. The red rectangle in the center is a gate. And those two crosses, those are the contact for the source and drain. And this rectangle indicates the N-type select, and the real active region is this one. This is the real active region, and it's shown as green color, right? Active, see active, it should be green color. That is exactly what we have over here. But on the left-hand side and right-hand side, it's overlapped with metal 1 contact. See, metal 1 is blue, right? So on the two ends, we have two contacts. So this is a transistor. And we can measure the dimension of the transistor using button K. So if you want to create ruler, that is button K. And we measure the dimension of the width. So from here, drag it down, the width is 1.5 micrometer. And now I measure the length of the gate. That is 0.6 micrometer, right? So, and I want to remove the ruler, remove ruler. I use button, let me try, yes, Shift plus K. So the ruler is gone. And I want to design a transistor with the size of 10 micrometer for the width and 1 micrometer for the length. So I select this cell, use button Q to bring out the property, and choose parameter. Under the parameter, I change the width to 10 micrometer and change the length to 1 micrometer. Okay, and click OK. See, now the layout is automatically updated. So it's really simple for us to do the layout, because this kind of cell is called P cell. P cell means parasitic cell. So the foundry already designed some smart computer software for you. You just need to specify the width and the length, then we get the transistor. However, we have the transistor, we have gate, source, and drain. And what is missing here? Yes, thank you. It's body. So I have to make contact from metal 1 to P substrate, right? That is body. I hit a button O. So in order to add contact, I use button O. And there we have all types of contact from metal 1 to P. P means P substrate. From metal 1 to polysilicon, from metal 1 to metal 2, and from metal 3 to metal 2. So I choose metal 1 to P substrate. And I can define, if I want 6 contact, I can change the number to 6. And here we go, we have the outline of the contact. I just put it over there. So that's all. And I have to make the connection. Remember that I tied the body together with the source, right? So what I have to do is go to LSW window, activate metal 1 layer, choose metal 1, and I add a path from this contact to the source. In order to add a path, I hit a button P. And click over here, drag it to the other side, and this is a path. So in order to add path, use button P. So now the body and the source has been taken care of. The other side is the drain. So let's assume I want to make a path to route out the drain signal. So I use button P again, extend it, and I can even make it weird. This is a real route, right? Something like this. And now I have to take care of my gate. For gate, because gate is made up of polysilicon, so I have to activate the layer of polysilicon, poly, and draw the path. Use P. It's a bit slow. Okay. And draw a path like this. Let's assume signal comes from this side. And finally, I have to add a contact for the polysilicon to route the signal into metal 2. Let's assume I want to use metal 1 to route the signal. So I make contact M1 to poly and add this contact over here. So that's all. And finally, I have to define the pins, because in the schematic I defined 3 pins: ground, GND, and the gate and drain, right? So in order to define pin in layout, I use Control plus P. So I hit Control plus P, gives me this window. And the terminal name, first of all, let's take care of ground. And I choose this, enable display pin name, so that I can see the name of the pin. And this pin is input output pin, and pin type is metal 1, because I'm using metal 1 for the signal route, metal 1. And now I move the mouse into the layout, put a pin over here, and move the label to the other side to make it look nice. And when the company fabricates a transistor, it will just skip this label. The label will not be fabricated. And I add the other pin for the gate. And this pin is input pin, still metal 1. So add the pin over here, metal 1. And the last pin, drain. and this is output pin, still metal one, so should be okay to do it like this. So now everything's set. And next is DRC, design rule check, right? So I go to verify here, click DRC, and simply click OK. The default setup is good enough, so click OK. After that, I can turn to the ICFB window. So in the ICFB window, it tells me DRC completed and the total error found is 0. That is good. So DRC, I have passed it. Next is extraction. So go to verify. Come on. Okay. Choose extract. Click OK. Yeah, it's done. And go to ICFB, it tells me total error 0. So that is good, means extraction is finished. So we go to library manager, we can see the extracted view, right? So I double click it. It opens the extracted view, and again I use Shift F to display everything. So in the extracted view, it shows me the outline of the layout and also overlapped with the component that the software can recognize. So the software can successfully recognize I have drawn an MOS transistor over here, right? And it also shows me the dimension of the transistor. Width is 10.05 micrometer, length is 1.05 micrometer, and I have 3 terminals, drain, gate, and ground, defined in my schematic. Defined in my layout. So that's all finished. I close it. I go back to the layout window. To finish the last step, go to verify LVS. I have to do layout versus schematic to verify that the layout is what I want in my schematic, because I always use schematic for simulation. So in the LVS window, we have to be careful about 2 entries. One is the schematic, one is the extracted view. We have to specify the correct cells we want to compare. So I click the browse under schematic, and I choose the thing I designed today, which is in the library of E4221, 5221, 5321 underscore demo, PMOS demo layout, and I select the schematic, close it, and see it's automatically updated. The cell is NMOS underscore demo underscore layout, and the view is schematic. So I do the same thing for the extracted view. I click browse and choose the extracted view I just generated right here. Close it. So now it's ready, and I click run this button to run LVS. Click OK in the pop-up. And within a little while, we should have the information window coming up. It tells me the LVS job has completed the net list match, which means the layout match with schematic, which is good. So close it. And I can also click the button output. And in the output window, we can see the summary of the LVS. So the summary tells me on the layout, the netlist from the layout, the software can identify 3 nets, 3 terminals, 1 NMOS transistor. And in the schematic, it can also identify 3 nets, 3 terminals, and 1 NMOS. And also it lists the name of the nets and the name of the components. And if you go down, it tells me the netlist match, which is good, and a summary of unmatched component, matched component, merged component. So of course, unmatched component number is 0. And we have active device, the total number is 1, and they perfectly match. So everything is good. So later on in your project design and in your homework, in order to show that your layout is correct, you have to print out this file in your report. Okay? And finally, let me give you a short example. If I made something wrong, what will LVS tell us? So let's assume I mistakenly left it open. It's not connected. Now I do extraction. Click OK. And after extraction, I go to LVS. And the setup is still there. The schematic extracted view is still there. So I just need to click Run. And now, after LVS is done, it tells me LVS job has completed, but the netlist failed to match. So if I open up the output, on the layout, it can still identify 3 nets, 3 terminals, 1 MOS, 1 MOS, also in schematic, but the correspondence is wrong. So if you go down on the document, it tells you what is unmatched. So here it tells us the nets, the merged net is unmatched. Okay? And of course, you will have the information the netlist failed to match. And from the details, you can figure out what is wrong. Okay? Alright, and we are running out of time. I'll stop here, and next week we will have another layout EDA tutorial. Thank you, and on Friday we will continue with our regular lecture. I'll see you on Friday.